multiplying image enhancement for the defect, characterization in XCT of carbon fiber composite parts. So yeah, as already Professor Lomov said, CT can be used for defect characterization, for finite element modeling, for a lot of purposes. But there is a limitation. Could you please move? Okay. So also there is also. Okay, let's do it like this. Okay, thank you. Okay, nice. Yeah. So there is always resolution versus size trade-off. So as already mentioned, to acquire high resolution images, you need very small space, like few millimeters in size. Or we can take larger specimen, and the resolution will be much lower. So this is its trade-off, and this physical limitation, especially seen in industry industry systems, where the resolution is not like few microns per pixel, can be up to 70, 80 microns per pixel. So even with this, and this is usually used for industry. And our purpose, our idea here is to take this industrial low quality CT images and increase this, their resolution with the use of machine learning techniques. And so basically, there is a term of super resolution where we have a low resolution image, apply this machine learning algorithm, and have a high resolution image. And already, this is a very developed field, but for two-dimensional images. But we cannot take these algorithms developed for 2D images and apply for our 3D image because there will be inconsistencies between slices. Because there are some variability between slice-to-slice generation. And this is why we want to have a three-dimensional generation. And we already tried this algorithm for automated fiber brick analysis. This was done with Catholic University Leuven. And we had good results. It was published, and here we tried to implement this methodology for industrial CT. So the idea is following: we have industrial CT and lab CT. From lab CT, we have very high quality images. From industrial CT, we have the images of the same specimen of the same spot, but in the lower resolution. Using these images, we train our super resolution model, and after that, we apply to the larger image, like of all the full part, to have a very large, high quality image of the full part. So this is the idea, and we had this. Images of carbon fiber reinforced polymer part. This is low quality, so yeah, I cannot see here. This is 75 microns per pixel. This is 28 microns per pixel, and you can see some defects already not seen on the industrial CT images, but on the lab CT we can see them. But they are not paired. So super resolution requires to be pixel-to-pixel registration. We tried to do it. Like we did a very rigorous registration process here with affine registration, CYN registration, where we use not degree of freedom, where for each pixel there is a vector where you should move, but even after this registration process, we had some deviations between these CT images. So this is pre-processing. After that, we did scale correction, split it into small volumes to fit into narrow network, filtered by anisotropy. And here's the example of our training dataset. We had around 5,000 points to train model on. And here's the model. So basically, the model consists of generation. So this is the model that do all the work. This model take low resolution images and give us high resolution images. And this discriminator is needed to make training process correct. So just basically implements comparison, is it generated or not? And lower generator is needed just to make unpaired training. So I will not go into details. If you're interested, we can discuss it. As just I showed that this also was rigorous process that involves a lot of computations. So this is the internal structure of the generator. This was taken a state-of-the-art GAN model, so it's already quite old. It's 2018, and here's the training parameters and the results. So as you can see from these very low resolution images, the model was able to reconstruct this one, and they're quite equal to this. On the first glance, we can see that it's okay. And we have checked that we did defect volume fraction assessment with simple thresholding. And this is a region of interest of the center of CT. And you can see that this is for low resolution images, it was 0.15. For super resolution, 0.27. And for high resolution, for original high resolution images lab, this was 0.33. So there is an enrichment, so this is good, but this was done by fine-tuning of the model. So just basically we took our model and we fine-tuned the parameters to have it matched the specimen. Why is that? Because for each of the new data, we have to go to this process again. And if we look to the parts of the image near the edges, we can see a lot of hallucinations. So this is the defect that was generated out of the water. So there is no, originally, there is no defects here, but they were generated. And they're not compared to the original images. It was much higher than it should be. So this is have two colors. The first one, that the industrial city images are quite noisy, and we should pay more attention to it. And we have to use better models, for example, diffusion or transforming new models. But for these new models, we need much more data. Like again, the main problem in deep learning works, the algorithms really depend on the data. So we propose to create to do in this institutional collaboration to create large-scale dataset of non-proprietary, so non-proprietary CT images covering diverse material classes and resolutions, create this benchmark dataset, of course publish data table or data article on this, and after that develop the super resolution. We plan to develop, based on this benchmark dataset, we plan to develop a super resolution model and make it open source to accelerate the development. Because without these open source datasets, the field will not develop. And yeah, and I move to conclusions. So basically, super resolution methods can bridge this gap between fast industrial scans and high quality border images, but we have to move to the more advanced algorithms, transformer or diffusion models, and for this we need more data. So basically it's this, and I hope in the future we will work on this together to develop super resolution algorithms. Thank you.